based on the completeness axiom and the definitions of supremum, infimum, etc., we will have a problem solving session now. So we are starting with the very elementary problem, that is the uniqueness of supremum. So the very first question is the following. Let A subset of R be bounded above. Show that supremum of A is unique in R. So remember that by the axiom of completeness, since A is bounded above and of course non-T, then we have to show that supremum of A is unique in R. So as in the case of many uniqueness problems in mathematics, here also we will use exactly the same technique. That means assume that there are, if possible, there are two numbers S1 and S2, both are supremum, and then finally we will come to the conclusion that S1 and S2 must be the same, exactly the same technique. Suppose S1 equal to supremum of A, or S1 is A, that's better because we don't know whether it is equal to S1 is A supremum of A and S2 is also a supremum of A. Now we are going to interchangeably using the properties of S1 as supremum and S2 as upper bound. So S1 supremum, S2 upper bound. Okay, because supremum we know that it's an upper bound also, but we know that supremum is going to be less than or equal to any other upper bound. Therefore, S1 less than or equal to S2. Now, if we reverse the roles, S1 upper bound, S2 supremum, then S2 less than or equal to S1. But these two together implies that, so these two together implies that S1 must be equal to S2. Therefore, supremum of a set, if it exists, is going to be unique. Exactly in the same way, we can show that infimum of a set, if it exists, is going to be unique. But of course, remember that we haven't shown, we haven't proved, or we haven't stated any axiom of completeness regarding the existence of infimum. That will actually follow from the next problem. So our next question is the following. Let A subset of R be a set that is bounded below in R. Define B is equal to the set of all real numbers that are lower bounds of A. That means that B is a set of all lower bounds of A. The question is to show that supremum of B is equal to infimum of A. So if we try to sketch, it looks probably like this. Suppose that, so the set A is somewhere here, A is here, and the set B is lying to the left of A. So what we have to show is that supremum of B is equal to infimum of A. For this, we are going to show that supremum of B greater than infimum of A is not possible, and supremum of B less than infimum of A is not possible. So we will assume first, if possible, assume that supremum of B is greater than infimum of A. For convenience, we may take this to be equal to S and this as L. Therefore, we are assuming that S is greater than L. Since S is greater than L, S greater than L equal to infimum of A, S is not A lower bound for A. So S is not a lower bound if it means that there exists A in capital A such that A less than S. So A is somewhere here and S is somewhere here, and the midpoint A plus S by 2 is somewhere here. This is the midpoint A less than A plus S by 2 less than S. Now, if B belongs to B, then B is a lower bound for A. Therefore, B must be less than or equal to A. Therefore, B less than or equal to A less than A plus S by 2 less than S. This means that this means that A plus S by 2 is an upper bound for B. So we have A plus S by 2 and upper bound for B. A plus S by 2 is less than S, where S is the supremum of B, and we are getting an upper bound for B which is strictly less than the supremum. But supremum of B equal to S is less than a very less than or equal to a very upper bound for B. But here we are getting supremum of B is equal to S, and S is greater than A plus S by 2, and A plus S by 2 is still an upper bound for B. This is a contradiction. Therefore, the supremum of B cannot be greater than infimum of A. Therefore, supremum of B must be less than or equal to infimum of A. Now we have to completely remove the possibility that supremum of B is less than infimum of A, so that the only possibility remaining will be supremum of B equal to infimum of A. So assume now that supremum of B is less than infimum of A. Now we use the same technique that we used in the previous step. Supremum of B, we called it as S, this we called as L. So S is less than L. Therefore, take the midpoint S less than S plus L by 2 less than L. Therefore, S plus L by 2, since it's less than L, is a lower bound for A. But then, since B is a set of all lower bounds for A, we have therefore S plus L by 2 is in B, but S is equal to supremum of B, and therefore S must be greater than or equal to every element in B. But here we are getting S plus L by 2 greater than S, and S plus L by 2 in B. Therefore, S greater than or equal to S plus L by 2. But these two things, these two statements cannot happen together, and therefore, which is a this is a contradiction. So we are getting that S cannot be, S is not possible. S is not possible. So S less than L is not possible. S greater than L is not possible. S greater than L not possible. S less than L not possible. So the only possibility remaining is S must be equal to L. Now we can prove an axiom, not actually an axiom, a result that is similar to the axiom of completeness that involves the existence of infimum for every bounded below set. The statement is precisely the following. Statement similar to axiom of completeness that a subset of R, a bounded below and a non-empty. Then A has an LUB or infimum in R. So we can actually prove this using the problem that we just now finished. For proving this, take B equal to all lower bounds of A. And then B is bounded above by any element in A. So since A is a non-empty set, there is at least one element in A, and since B is set of all lower bounds of A, if we take at least one element from A, that will become an upper bound for B. Therefore, B is bound above by any element in A. Therefore, by the axiom of completeness, B has a supremum in R. But by the problem just now, we proved supremum of B is equal to infimum of A, and therefore we can say that the set A, which is bounded below, has an infimum. Now it probably becomes obvious that why we didn't want to call this axiom of completeness in terms of LUB also. Basically because we can actually derive the similar statement for the LUB just using the axiom of completeness for the supremum. And since an axiom cannot be, should not be derived from another existing result, we cannot call the statement just now we proved to be again an axiom. So axiom of completeness is only related to the supremum, or in fact we can take the axiom to be only related to infimum, and then we can derive the similar statement in the case of supremum also. Now we have one more question. Suppose A subset of B in R, then show that supremum of A less than or equal to supremum of B. Let A belongs to A and S is equal to supremum of B. Now A belongs to A and capital A is a subset of B implies that A belongs to B also implies that A is less than or equal to S. Let S1 equal to supremum of A. So we have to show that S1 is, we have to so that S1 is less than or equal to S. If S1 is greater than S, then S is less than S1, and we again find the midpoint is less than S plus S1 by 2 less than S1. So S plus S1 by 2 is not an upper bound for A, since supremum of A equal to the symbol we have taken is S1, and S plus S1 by 2 is less than S1. So supremum is the least upper bound, therefore anything less than that cannot be an upper bound, therefore S plus S1 by 2 is not an upper bound for A. So there exists an element A in capital A, that this is not an upper bound, therefore S plus S1 by 2 is less than A. But A in capital A implies A in B also. Now, supremum of B equal to, now we have taken that to be equal to S, and S is less than S plus S1 by 2, but we are getting this to be less than A, but A belongs to capital B. So here we are getting a contradiction that supremum of B is less than an element in B. This is a contradiction. This results into a contradiction. It's a contradiction since we are getting an element to be greater than the supremum, and therefore what we assumed must be wrong. And what is the assumption? Here we assumed that S1 is greater than S, that must be wrong. Therefore, for S1 is less than or equal to S. So we establish what we claimed.